Acids, I tell you, trippy stuff. That is a hell of a chemical. You take an acid and you put it on stuff and it just eats it away. Hell of a chemical. So what is it? What is an acid? And how does it even do that? How does it go about breaking something down? All right, let's define an acid. An acid is any chemical that when you put it in water, it produces hydrogen ions. So little H pluses float around in the liquid. Now, those H pluses floating around in the liquid is what makes an acid so potent. Those are the active ingredients in an acid. Those H pluses are the things that chemically react with other things and break them down. So what makes an acid strong, what makes a certain acid so good at breaking things down, is their ability to produce those H plus ions. Certain chemicals produce a whole bunch of them, other ones produce a couple. Like vinegar, considered a weak acid because it produces a few H plus ions when it's inside of water. Other acids are incredible at breaking things down. There's strong acids out there, like the stuff in your stomach, that's hydrochloric acid. That stuff produces so many H plus ions that you bring anything organic near that stuff and it just starts ripping it apart. Hydrofluoric acid, sulfuric acid, there's tons of these just super dangerous things. And what makes them so effective is their ability to produce an astounding number of H plus ions. And then that huge number of attack chemicals can break things down really effectively. Now, bases are nothing that you want to shake your head at either. Those things are equally as powerful, but they're a different molecule. Bases tend to be the opposite of acids. What makes a base is that chemical's ability to produce OH ions. They're called hydroxide ions. It's a combination of oxygen and hydrogen bonded together. Now those hydroxide ions floating around inside of water have the same destructive power as H plus ions. They will bind to things and rip them apart. So weak bases are ones that produce a few hydroxide ions, and then strong bases are ones that produce a heck of a lot of hydroxide ions. Acids and bases, they're opposites of each other. Acids produce H plus, bases produce OH negative. Acids and bases. We can measure acids and bases using a scale. It's a special scale called the pH scale. So a pH scale is kind of like the Richter scale for earthquakes, if you remember how that works. It's logarithmic, which means that it is every jump from, say, 1 to 2 or is a change by a factor of 10. So pH stands for power of hydrogen. This is our way of measuring the strength of an acid in base. So the power of hydrogen is a direct measurement of the amount of hydrogen ions inside of an acid. So the neutral level, where it's not an acid, where it's not a base, is at the level 7. Acids are everything below 7. Bases are everything above 7. So when you start looking at numbers like 0, 1, 2, or 3, you're looking at strong acids. When you're looking at numbers like 13, 14, 15, you're looking at chemicals that are strong bases. A pH of 7 is considered neutral because it is in a 1-to-1 ratio of hydrogen ions and hydroxide ions. So the H pluses are in equal portions to the OH negative portions. So neither chemical has influence over the other one. So like they're not in greater numbers. So it's neutral. It doesn't have the ability to eat away at things. As you change, as you go to from 7 to 6, you have 10 times more hydrogen ions than hydroxide ions. 10 times more. When you go from 6 to 7, that is another 10 times, for a total of 100 times more than a neutral substance. From 5 to 4, it's another 10 times. From 4 to 3, it's another 10 times. And I think you can quickly see how as you go from 3 to 2 to 1, you start getting some hugely potent chemicals. Hydrochloric acid in your stomach has a pH of 2. It is super acidic. It's the same way, the other way, when you're looking at bases. As you go from a 7 to an 8, you have 10 times more hydroxide ions than hydrogen ones. As you go from an 8 to a 9, you have another 10 times hydroxide ions, for a total of 100 times more hydroxide ions. So this is the pH scale. From anything below 7 is an acid, anything above 7 is a base. Let's look at this neutral zone. It's pretty cool here. In the neutral zone, like at the pH of 7, there's some pretty impactful things here. Let's look carefully at that idea of taking H plus ions and having them in equal portions to OH negative ions. In fact, let's chemically react the two of them. We're going to take H plus, chemically combine it with OH negative, and look at what we get. We got 2 hydrogens coming together with 1 oxygen. Bum, 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 water! That's a neutral substance. In fact, water is the neutral substance. Water, by its very definition, is a pH of 7. It is a neutral, it is the neutral substance. So acids and bases can actually neutralize each other. If I took a strong acid, say it was at a pH of 2, and I combined it with an equally powerful strong base, like sodium hydroxide, which has a pH of around 13, if I were to combine those two equally powerful acids and bases, and I were to mix them, look at the chemicals that can come out. I take hydrogen and chlorine, split apart, and I take sodium and hydroxide, split them apart, and combine it all together in one big mixture. I get water and salt. You bet I could take hydrochloric acid and mix it with sodium hydroxide, and if I did it in an equal portion of equal strength, I'd just have a drink of salty water. How amazing is that? In fact, if you really want to get specific with the definition of a salt is any solid that's produced from an acid-base reaction. So the salt, the table salt that we're accustomed to, isn't the only salt that exists. If you were to combine other things, other acids with other bases, and when the H and the OH from the acids combine together and neutralize each other, there's something else that combines, and that chemical is always called a salt. So just to clarify, one burning question. Is everything an acid and a base? No. Only chemicals that are associated with H plus or OH negative fall somewhere on the pH scale. If you were to look at, say, oil, it doesn't have a pH because it's not associated with water. Remember, oil and water are insoluble. They don't mix. They separate away from each other. So oil, having nothing to do with water, also has nothing to do with acids and bases. So not everything can be an acid and base, but if there is H plus in there, or there's OH negative, or there's even the possibility that that can come out of a chemical from even a series of chemical reactions, then you have an acid or a base. And they're numerous. There's lots of them. Let's compare some of the characteristics of acids and bases. Acids, remember, have those H+ ions. They are sour to the taste. In fact, most of the food you eat is acidic in some form or fashion. They also kind of have a sticky feel to them. If you were to feel an acid, bases are a little different. Bases have a bitter taste to them. They have those hydroxide ions, the OH negative ions, and they tend to have a slippery feel to them. Like if you've ever used any cleaning products around your house, usually those are bases. If you feel the chemical directly at all, it feels slippery. It feels kind of weird. So acids and bases, they have different characteristics, and some that are kind of specific to their brand. So how do we tell if an acid or a base is present? We have created a couple different tests that test for the pH level. They test for how acidic or how basic something is. The most classic one is litmus paper. There's two different types of litmus paper. There's red litmus paper and blue litmus paper. Now, red litmus paper is characteristic of acids. Blue litmus paper is characteristic of bases. If you were to take red litmus paper and put it inside of an acid, it will stay red. You put it inside of a base, it turns blue. If you do the opposite, if you take a piece of blue litmus paper and put it inside of blue litmus paper and put it inside of an acid, it turns red. If you take a base and put it inside, or if you take a blue litmus paper and put it in a base, it stays blue. Now here's the catch. If you were to take a piece of litmus paper, both red and blue, and you were to dip it in a substance, and both of them came out their same color, then you have a neutral substance. If it's neither acid or base, it won't change the color of either of them. And you can try that with water. There are other indicators. It's not just little pieces of pH paper, but things like phenolphthalein and bromothymol blue. They're used to detect acids or bases at more specific levels. So acids and bases, they clearly are something of concern, especially strong acids and strong bases. We don't want them introduced into environments because they have the potential to really mess things up. Imagine an acid being introduced inside of a lake. If it becomes too acidic, like we've seen with eggs, if you take an egg and put it inside of vinegar, a weak acid, vinegar is a fairly weak acid, you put an egg inside of vinegar and the shell dissolves, there's organisms that lay eggs in water. Fish. If water is acidic, when fish lay their eggs die. That's obviously not a good thing. So how does acid end up in rivers, lakes, and ponds? The rain. We know that certain chemicals, when they're up in the air, they make acid rain. Like sulfur dioxides, things that we release from burning fossil fuels, nitrogen dioxides, carbon dioxides, like those are things that we make from burning fossil fuels, and they go up in the air, they dissolve inside of water, and then produce acids. And then those acids come pouring down into our rivers, lakes, and ponds, and in a high enough concentration, if they introduce enough H+ ions into the water, they can totally mess things up. Fish is just the start of it. We live in like the Arctic tundra up here in Fort McMurray in Canada. Oh man, so much snow comes on down, and that snow can hold the same acids as rain, but it stays there. It stays as snow for a long time until spring comes around. and then something catastrophic can happen. If that snow holds enough acid inside of it that when it all melts, it all gets introduced into a lake or a pond at the same time, you can end up with something called spring acid shock. It's exactly what you would expect. So much acid introduced all at once, ecosystem collapses all at once. Scary stuff. Spring acid shock at almost the minimum will disrupt fish from being able to properly create offspring. So, our pollution. We, again, just keep coming back to the same idea. We have to be aware of what we're putting up there. And we have to look at the long-term effect of these chemicals because they have an effect. A measurable, calculatable, observable effect that we know is happening and we know we have to deal with. Aside from ecosystems, there's the other side to acid rain. It can also destroy our stuff. Like acids can break down things like limestone, granite, other things that we use to build our buildings. Acids slowly eat them away. We don't want our buildings being eaten away. We don't want our parks damaged. We don't want anything human to be damaged because that costs money, it costs time, it costs happiness in an overall area, and these are all things that the government needs to be aware of and help prevent from happening. And so we at this really interesting kind of bottleneck. How much do we regulate these chemicals while at the same time making sure that our economic prosperity exists as well? Tough battle between the two. We need to, we can't completely walk away from fossil fuels all at once. We want to, and we're trying. We're creating lots of green technologies, but we can't drop it all at once. That's unfeasible. We will end up with financial collapse of our country. But at the same time, we know we have to. There is no working around it. We are really messing up lots of things. So, interesting conversation. There is no right answer right now. Let's summarize our conversation about acids and bases. Acids are chemicals that produce H+ ions inside of liquids. Those H+ ions are very reactive and they have the potential to really rip things up. So we measure the amount of acidity of something based on the pH scale. 7 on a pH scale is neutral. Anything below 7, which can even go into the negatives, even go to 0. Anything below 7 is a acid. Anything above 7 is a base. Bases, again, are the OH negative ions. So any chemical that produces hydroxide ions and can introduce that into a liquid. Those are equally as damaging as H+ ions. A neutral substance, by definition, is water. It is the combination of an acid's H+ and a base's OH negative. Those two come together and they form water. Again, that is what makes water the perfect 7. It is the very neutral substance. So beyond that, there's characteristics of acids and bases. They, like acids, they're sticky to the touch, they taste sour. Bases, they're slimy to the touch and they taste bitter. We can find out if something's an acid or a base using indicators. Litmus paper, red and blue litmus paper, tend to be our go-to. If you want to find out if something's acidic, you can use red and blue litmus paper and test and see if it changes the color of the paper. Litmus paper turning red is acid, litmus paper turning blue is a base. And then finally, acids, they have the ability to mess up our ecosystems. We produce, as a human race, we produce chemicals that go up and make acids inside of our rain. And then that rain can come down and damage things, as I went through, like spring acid shock. A scary thing that is very real and has done in many ecosystems. So lots to consider, acids and bases. Now you know all about them. Thanks so much for watching. Till next time.